Hello everyone, welcome back to my organic chemistry mini lecture. Today our topic will be the calculation of radical yield. Um, we will focus on two reactions, chlorination and bromination. And you may notice that we have a reaction, the butane react with chlorine molecule under light. So this is a hint that the reaction is a radical reaction. There are two possible products could formed. One is the 2-chlorobutane, and that is secondary hydrogen be replaced by chlorine, or the 1-chlorobutane. So that's the primary hydrogen can be replaced by the chlorine. Now you could have faced a question like this: what is the expected percentage of the two product? What's the yield? What's the yield based on calculation? So how to do that? First, we can identify the 10 hydrogens in this butane. Here, I just draw the expanded structure, make it easier to see. And also, we need to know the concept of the reactivity ratio. For chlorination, the primary hydrogen and the secondary hydrogen and the tertiary hydrogen, the ratio is 1 to 3.8 to 5. For bromination, the reactivity ratio is the primary hydrogen to secondary hydrogen to tertiary hydrogen is 1 to 82 to 1,600. So these different number based on the stability of the radicals, okay, because the tertiary radical is more stable than secondary radical is more stable than primary radical. And also, the bromination is more selective, you can see, than the chlorination. That's because the thermodynamic reason. Okay, so now let's go back to the calculation, how to calculate the percent yield. And if you look at this product, the chlorine will replace one of the secondary hydrogen. If you look at this expanded structure, there are overall 4 of the secondary hydrogen can be replaced. So each of them, okay, any one of these 4 hydrogen can be reacted and can be replaced by chlorine to form the same product. So we can use 4, that's the total possible hydrogen can be reacted, times the relative reactivity. Because it's a chlorination, we use this data here, and that's a secondary hydrogen, so we will use 3.8 for secondary. And now it will divide it by the total possible all the hydrogens reactivity. So we have 4 secondary hydrogen times 3.8, and we also have 6 primary hydrogen. 1, 2, 3, 4, 5, 6. That's basically the 2 methyl group. So 6 times 1 is reactivity of the primary hydrogen, 1. So we can do the calculation here. So that will be 15.2 divided by 21.2, that is 71.7%. Now look at the other possible product. The chlorine will replace one of the primary hydrogen. We have 6 equivalent, means they are basically symmetric and they are same environment. This is 6 hydrogens. Any one of them can be replaced by the chlorine to form the same product. Okay, so now the calculation is 6 times 1. We have 6 possible hydrogen can be reacted, times 1 is relative reactivity, over the denominator will be the same. So all the possible, okay, 4 times 3.8, that's the secondary hydrogen, and the 6 primary hydrogen. You have to multiply with the reactivity, okay? And then we can calculate the ratio as 6 over 21.2 is 28.3%. So that's how you calculate the radical yield of this chlorination of butane. Now let's look at the bromination. So I'll use the exactly same reactant, the butane, react with bromine molecule under radical conditions. You could also have two possible products, the 2-bromobutane and the 1-bromobutane. And what is the percent yield? Okay, so same idea. We just use the same strategy, and we also need to use the bromination data. Okay, here, not chlorination, because the bromination this time. So bromination, we have this different reactivity. For this 2-bromobutane, we can use the 4, because any of the 4 hydrogen can be replaced by bromine, form the same product. 4 times 82. Now this time is 82 because for bromination, the secondary hydrogen, the reactivity is 82. Then divided by 2, that's the secondary hydrogen. 4 times 82 plus there are 6 primary hydrogen times 1. So this time is different number. So that will give you 98.2%. And then for this 1-bromobutane, we need to use 6 because any one of the 6 hydrogen can be replaced by bromine times reactivity, that's 1, over the same denominator, okay, as this one. And then you can calculate 6 over 334 is 1.8%. So again, you can see the bromination is much more selective than chlorination. Okay. Now I'll give you another example that is the acyclic alkane, and chlorination reaction could give you 4 different reactions. Okay, so that is this 4. So if you have the chlorination to this methyl or this methyl, okay, or this carbon, that's methine, okay, or this carbon, that's the methylene, or this carbon, okay, so that's another methylene. They are different product. And what is the percent yield? So now we can use the same strategy to calculate it based on the reactivity ratio. Okay, now we can draw the a little bit more detailed structure, shows the hydrogens. And now for and again, we need to use the data here. Okay, so for the chlorination, remember we need to use this reactivity ratio here. Okay, now for this first, the product, how many hydrogen can be replaced by chlorine to form this product? I will say 6 of them, right? Because this methyl and that methyl are symmetrical. That's why you can replace total any one of the 6 hydrogen. Okay, so you can use 6 times 1. 1 is the reactivity over total. Okay, that will be 6 primary hydrogen times 1 plus there are 6 secondary hydrogen. That's 2 plus 2 plus 2 here. That's 6 secondary times 3.8. 3.8 is the secondary reactivity. And now you have 2 tertiary, okay, hydrogen. So 2 times 5. Now you can calculate the number 6 over 38.8. I'll give you 15.5% of this product that's expected. Now for this second product, how many hydrogen can be replaced by chlorine? I will say 1 or this one. Okay, so that's 2. Now reactivity is 5 over same denominator, same as the first calculation. Okay, so now you can calculate, that's 10 over 38.8, that is 25.8%. Now the third product, how many hydrogens can be replaced by the chlorine? I will say 4 of them, either this methylenes or this methylenes hydrogens. So not this one, okay? So because only these 2 carbon or these 2 methylene are symmetric. So that's 4 times 3.8. 3.8 is the reactivity of the secondary hydrogen over same denominator. And then you calculate the percentage is 39.2%. Now last one, how many hydrogen can be replaced by the chlorine? And only this 2. Okay, so I just want to clarify that when we calculate the percent yield, we are not considering the stereoisomer, or we just assuming you will make a racemic mixture if you make enantiomers. Okay, so now we have just the 2 hydrogen can be replaced by chlorine, 2 times 3.8 over same denominator. Okay, you can calculate the percentage is 19.6%. Okay, give you one more example, and again, bromination, and I'll use different reactant. This is a 2-methyl-butane. And the bromination, again, will also give you 4 different possible product. And again, you need to calculate percent yield. Okay, so we follow the same strategy again. So we can draw the hydrogens and in this condensed structure, and then also we need the data. Now this time we need this bromination reactivity. For this first product, you can look at this condensed structure. I will say you could replace one of the 6 here, 3 here, 3 here. The 2 methyl group are symmetrical. So, and any one of the 6 hydrogen, primary hydrogen, can be replaced by bromine to form this first product. Okay, you cannot do this, replace this one, because that will give you different product. That will be the 4th product. Okay, for this product, you could have 6 primary hydrogen can be replaced times 1. That's the relativity, reactivity. Over, we have, now we have to calculate the total primary. That's actually 9. 3, 3, and 3. That's 9 primary hydrogen times 1. Plus, there are 2 secondary hydrogen here. So 2 times 82. 82 here. Okay. Plus 1 tertiary carbon hydrogen. So 1 times 1,600. Then you can calculate that number is 0.34%. Very little. Now for the second product, the only one of this tertiary hydrogen can be replaced. You don't have any other possible hydrogen can be replaced. So that's only 1 times 1,600 over the same denominator with the first calculation. So I will just do the calculation, and that's 90.2%. Very high percentage. Now for this bromide, the third product, we have only this 2 hydrogen can be replaced. So 2 times 82, that's a secondary hydrogen, over same denominator. So you can calculate that is 9.2%. Last one, bromination on this carbon, you can only replace one of the 3 hydrogen here. That's 3 times 1 reactivity over same denominator. And then the calculation give you 0.17%. Okay, so again, you can see the bromination is much more selective. This is the major product is more than 90% as expected, okay, based on your calculation. Okay, so that's all the examples I want to give you. And but if you have any questions, then please let me know. Okay, so good luck.